Our first problem is 4-131 from the book. The problem statement I've summarized here on the first slide. We have two rigid tanks connected by a valve. You see tank A and tank B, and here's the valve. The initial state of the tanks are given, so we have 0.2 cubic meters of water at 400 kPa and 80% quality in tank A, and we have 0.5 cubic meters of water at 200 kPa and 250 degrees C in tank B. We're then told that the valve is open and the tanks reach the same state and thermal equilibrium with the surroundings at 25 degrees C. And what the question asks us is, what is the final pressure and what is the total heat transferred to or from the system? Okay. So the first thing I'm going to do is define my system. So I'm going to define this as the content of the tanks. So all of the water inside the tanks. I'm just showing the system here. I'm going to neglect the material of the tanks themselves. I'm going to neglect the material inside the connecting line and the valve. So I've defined my system as the water contained in tank A and tank B. Now, I'm going to list my assumptions. I'm going to assume that no work is done on or by the system. I'm going to assume, as I said, neglect water in the connecting line. And the valve. And I'm going to assume it's a closed system. So the mass I start with is the mass I finish with. No mass in or out. Okay, so now my approach. Let me summarize my approach to how I'm going to solve this problem. I'm going to find the final state. So after the valve is open and the contents are allowed to reach equilibrium, both with both tanks and the surroundings, I'm going to find out what that state is finally in the tanks. I know my final temperature. So what I need to find is the final pressure. I'm going to do that by finding the final specific volume. I'm going to do that by finding the total mass of the water. Then I'm going to use the first law. To find Q, my heat transfer. Okay, so let's start. We're going to start here by finding the mass. Okay, so initially, and as we, just a reminder, since it's a closed system, initial mass equals final mass, which equals the mass of tank A plus the mass of tank B. And that's a plus sign. Okay. Let me see if I can redo that guy. Okay. So we're going to find the mass of tank A and mass of tank B initially, and that's going to be our total mass, initial and final. Okay. So mass of tank A. To do this, I'm going to first go to table A5, which, to remind you, is our saturated liquid vapor table for water. And I'm going to look at the properties at 400 kPa. There I see that the specific volume of saturated liquid is this value. And the specific volume of saturated vapor is this volume. So look in your table and make sure you find the same values as I do. So now what I can do is I can say, okay, my average, I know, just to remind you, in tank A to begin with, I have an 80% quality mixture. That means I have a mix of saturated liquid and saturated vapor. Okay, so knowing that, I can find what my average specific volume is by using this equation. Write that a little neater. Okay, I'm going to plug in these values. So this is my 80% quality, means X equals 0.8. So 1 minus X is 0.2. So when I plug in these values, right to the edge there. And when I solve this, I get and since I'm right on the edge of my screen here, I'll just tell you, let me erase this. My units are a little messy here, but still pretty messy. But my V average, my average specific volume, is 0.37210 cubic meters per kilogram. Okay, next thing I'm going to do, go to a new screen here, and now I can find the mass of tank A. Okay, and how am I going to do that? I'm going to use the average specific volume that I just found and the volume of the tank that I'm given in the problem. So that's going to be 0.2 cubic meters over the average specific volume we just found on the previous slide, which was 0.37210 meters cubed per kilogram. And when I solve that, I get 0.537 kilograms of water in tank A. Okay, now I need to do the same thing for tank B. So now I need to find the mass of tank B. Okay, and I'm again going to go to, I'm going to go to table A4, because remember let me keep erasing that, a little messy. Because just to remind you, the way that we find our state is to go to the saturated liquid vapor tables first, see if we're within the range of saturated liquid, saturated vapor, or somewhere in between. And that will tell us if we are saturated, saturated mix, subcooled, or superheated. Okay, so from table A4, we find that the initial pressure of tank B is less than the saturated pressure at the given temperature of 250 degrees C. Oops, that's a degree. So, we are superheated. Okay. So, and just a reminder, just a little side note, or you could go to table A5, where we tabulate again, our our saturated liquid vapor properties, and we could see that our initial temperature of B is greater than our saturation temperature. Oops, that's saturation temperature at 200 kPa. So we can use either one, but it gives us the same conclusion. So we're superheated. Okay, so now we go to our superheated table. So from table A6, we find our specific volume at 200 kPa or 0.2 megapascals, and at 250 degrees C. And we find that that is equal, from the table, to 1.19890 cubic meters per kilogram. Okay, now we can find the mass of tank B. Same way we did for A. We're going to say MB equals the volume of B over V. And when we plug in those values, it's 0.5 cubic meters over the value we just found, 1.19890 cubic meters per kilogram. And when we solve for that, we find that we have 0.417 kilograms of water initially in tank B. Okay, now to the next slide. So now we know that the total mass of our system, which, to remind you, we defined as the water in tank A plus the water in tank B. We're going to call this M sub T equals MA, the mass initially in tank A, plus the mass in tank B. So that is 0.537 plus 0.417 equals 0.954 kilograms. Okay, so this is our initial total mass and our final total mass because we have a closed system. Okay, so now we can say at the final state, we can find our specific volume. And we can do that because we know that the total volume equals, it does not change. It's the volume of tank A plus the volume of tank B. And we know that the mass doesn't change. So we're going to say this is total volume. Oops. That's a T. Over total mass. So that's going to be 0.7 meters cubed over 0.954 kilograms. And that value is 0.733 cubic meters per kilogram. Okay. Next thing we're going to do is we're going to take what we know about the final state, and we're going to take the specific volume that we just found to find our the final state of our water. Okay. So what we need to do is find our final specific volume on our tables. Okay. And we know two things now. We know our final specific volume and we know our final temperature. So we know enough to define the state. So we're going to go back to table 4, table A4. And at 25 degrees C, which we know is our final state, we find that saturated liquid specific volume is 0.001003 cubic meters per kilogram. And the specific volume of our saturated vapor is 43.340 cubic meters per kilogram. Now, we look at our value that we just calculated, and we see that we, at our final state, are in between vapor, saturated liquid, and saturated vapor. So, we have a mix. Okay? So, we know now that we have a saturated vapor liquid mix. All right, the next slide. So, we know a couple things. We know something now. We know we have a saturated, so therefore we have a saturated liquid vapor mix. And we know our pressure, because we know we're at the saturation pressure at 25 degrees C. So we know our final pressure is 3.17 kPa. And so make sure that you see that same value in the table that I found. All right, so now, okay, so now to find Q, we're going to set up the first law. For our system. So, for our closed system, we have the change in total energy of the system. I'm going to break this apart in just a moment, but we have our general form is change in energy of the system equals Q minus W. Now remember that the total energy of the system includes the change in the total internal energy, plus the change in potential energy, plus the change in kinetic energy, all of our system. And we're going to assume, additional assumptions here, that these are negligible. So, our first law expression becomes change in total energy of the system equals Q minus W. And remember that we assume no work being done on or by the system. So that goes away. And we end up with simply change in internal energy of the system equals the heat transfer. Okay. So this is the first law that we're going to use now to evaluate our heat transfer. Okay, to the next slide. So now we need to find our U. And if you remember, well, we need to find our change in U. So this equals our final internal energy minus our initial internal energy. That is a U there. Let's see. And that is going to equal the total mass of the system times the final specific internal energy minus the initial specific internal energy. Okay, so we know this. We already know that guy. We know that guy. So we need to find these two. And we're going to go back to our tables to get those values. Okay, so to find our U average at our final state, we're going to go back to the equation that allows us to find average properties for saturated mixes. Okay. Now, we can find these values. We can find these values from the table, the same spot we found our specific volume values before. So we're going to go back to table A, 4, and we're going to find that, our specific internal energy for saturated liquid is 104.83 kilojoules per kilogram. Our U for our saturated vapor is 2,409.1 kilojoules per kilogram. Okay. And again, these are values found at the final state, so this is the saturated state at 25 degrees C. Okay, so now what we need to find is our X. Okay. We can do that from the V average that we already found. Remember, X is our quality. So we're going to find our quality from our V average at the final state. Okay, so as a reminder, this is V average equals 1 minus X, V liquid plus X, V saturated vapor. Okay, I'm going to plug those values in, so I'm going to put in 0.733 cubic meters per kilogram equals, now remember, X is what we don't know, so it's going to be 1 minus X times the values that we found before from the table, so 0.001003 cubic meters per kilogram plus X times 43.340. And you can go back to the previous slide and you'll see those numbers. Okay, so I'm going to go to the next slide. From that calculation, I get that my final quality is 0.017. And again, I just calculated what we saw on the previous slide. All right, now I'm going to plug that quality in to my calculation for specific internal energy. Okay, so this is I'm mixing subscripts a little bit, but the subscripts I'm using, these are the average. This means that this is the average value for a saturated liquid vapor mix. And this little F for me just means final, so I'm just referring to the final state. Okay, so now I'm going to plug in. So I'm going to say 1 minus my quality, 0.017, times the specific internal energy for the liquid that we just found and wrote on the previous slide. And then I'm just running out of space here, so I'm just going to write on the second line. So plus the quality, 0.017, times the specific internal energy for the saturated liquid, that again we found in the table and wrote on the previous slide. So 2,409.1 kilojoules per kilogram. Okay, so when we calculate that, what we get is that our average final specific internal energy is 143.75 kilojoules per kilogram. And our total final internal energy equals that 143.75 kilojoules per kilogram, times the mass of the system, which to remind you is 0.954 kilograms. And so our final internal energy of our system is 137, let me write that a little neater, 137.1 kilojoules. Okay, so now we're almost there. We still need to find the initial total internal energy. Okay, which is going to be our mass. Let me rewrite that actually. Which is going to be our total internal energy of tank A plus our total internal energy of tank B, which is going to be the mass of tank A times the specific internal energy of tank A plus the mass of tank B times the specific internal energy of tank B. Okay, we're going to go to the next slide, and we're going to calculate these out. So, let's find the initial total internal energy of tank A, which again is mass times specific internal energy of tank A initially. So that's going to be our mass, our 0.537 kilograms. Again, that's the mass that was initially in tank A. And then I'm going to calculate the specific internal energy the same way I've been doing it for other saturated mixtures. So to remind you, this was an 80% quality mixture. So we have, oops. Again, I'm running out of space here, so I'll go to the next line. Okay. And again, I'm writing the same basic form of this equation over and over again, but just to remind you, this is an average specific internal energy calculated using 1 minus the quality times the specific internal energy of the saturated liquid plus the quality times the specific internal energy of the saturated vapor at the initial condition of tank A. So you should be able to go to the table and find these values that I found using the initial state of tank A. Okay, so we calculate all that out, and what we get is the total initial internal energy of tank A is 1161.7 kilojoules. Okay, last thing we need to find is the total initial internal energy of tank B, which is equal to mass times the specific internal energy of tank B, which is a superheated mix, so we don't need to use the quality in this case. It's a superheated vapor. So we know the initial mass, 0.417 kilograms, and we can go to the table for the initial state of, table A6 for the initial state of tank B, and find that the specific internal energy is 2,731.4 kilojoules per kilogram. We calculate that out, and the initial internal energy of tank B is 1138.99 kilojoules. Okay, going to the next slide. Now we have everything to figure out that our initial internal energy of our system, again, is equal to UA plus UB. So that is 1161.7 kilojoules plus 11, I'm just going to keep the correct sig figs here, 1139.0 kilojoules. And so U initial equals 2,300.7 kilojoules. Now let's go back to our statement of the first law, and we are ready to find our heat transfer. Plugging in our numbers. And this is our heat transfer. Okay, I hope that you have found this example useful, and just a reminder, as you follow through, go to your property tables and make sure that you can find the same values that I've found, and that you understand the flow of the process to solve this.